Welcome back, and in this lesson I want to discuss some advanced routing concepts which become important when dealing with complex hybrid networking. Now let's quickly refresh our knowledge before we move on to some of the more advanced routing topics. So subnets are associated with one route table only, no more and no less. And that's either an implicit association with the main route table of the VPC or a custom route table that you explicitly associate with a subnet. So you can create an explicit route table and you can associate it with a subnet, and when you do that, the main route table is disassociated. If you don't explicitly associate a custom route table with a subnet, or you remove an explicit association, then the main route table is associated again with that subnet. Now, route tables can also be associated with an internet gateway or virtual private gateway, and this allows them to be used to control traffic flow entering a VPC, either from the internet or from on-premises locations, and I'll be talking about that in more detail later in this lesson. Another important thing to understand about route tables is that IP version 4 and IP version 6 are dealt with separately, both in terms of default routes and more specific routes. At a high level, routes have two main components, a destination and a target. Now, the destination can either be a default destination, a network inside a notation, or a specific IP address also using a CIDR notation. And the destination is used by the VPC router or a virtual private gateway or internet gateway when it's evaluating traffic. And in addition to the destination, there's the target, and this configures where traffic should be sent to if it matches the destination. Now, a route table has a default limit of 50 static routes and 100 dynamic routes known as propagated routes, and this is per route table. So 50 routes that you statically add to a route table and 100 routes which are propagated onto that route table if you enable that option. Whenever traffic arrives at a VPC router interface or an internet gateway or a virtual private gateway interface, it's matched against routes in the relevant route table. All routes in a route table which match are all evaluated, and there's a priority order, and the one which matches and has the highest priority is used to control where traffic is directed towards. Now, visually, this is how route tables work from a subnet perspective. We start with a VPC, and it's a simple one with 4 subnets. Now, by default, a VPC is created with a main route table, and this is implicitly attached to all subnets within that VPC. Now, you can create other custom route tables which can be assigned to subnets within a VPC. Let's assume the top right one. When you associate a custom route table with a subnet, the main route table association is removed and the new custom route table is explicitly associated with that one single subnet. Now, subnets always have one and only one route table associated with them. If the custom route table is ever disassociated, then the implicit main route table association is re-added. It's not possible to have a subnet without a route table association. The default is that the main route table of the VPC is implicitly associated with all subnets. Now, when route tables are associated with subnets, this controls how traffic is handled when it arrives at the VPC router. Route tables can contain 2 different types of routes. We've got static routes and propagated routes. Static routes are added manually by you to a route table, and propagated routes are added when you enable this option via a virtual private gateway. So any routes that the virtual private gateway learns of will be added as dynamic routes onto the route table if you enable route propagation on that route table. So it's an option on a per route table basis that you can either enable or disable. And if you enable it, then that route table will be populated with any routes that the virtual private gateway becomes aware of. So these might be routes learned from Direct Connect or site-to-site VPNs, either using BGP or statically defined within the VPN configuration. So at a high level, whenever traffic exits a subnet, that subnet's route table is evaluated. The routes are all analysed looking for any which match the destination of the IP traffic, and for any which do match, an evaluation process is started. Now, if there's only one valid route which matches the destination of the traffic, then that route is used to control where to send that traffic to, so the target. That's nice and simple. If there's more than one route which can apply, then the first rule applies, and that's longest prefix wins. So a route with a /32 wins over a route with a /24 or a /16 or a /0. The higher the number after the slash, the more specific the route is, and a /32 represents one single IP address. So more specific routes always win, regardless of how they ended up on that route table. And if one route can be selected just based on this prefix, then that route is used. Now, if you have multiple routes which could apply and they all have the same prefix length, then the next step of priority is that statically added routes take priority over propagated ones. Static routes, remember, are ones that you add to a route table. And the logic to this is that if you've added something explicitly to a route table, then it is important and it should be there, and it should be preferenced versus anything which is dynamically learned from other entities in AWS. So if you have a route table which has a static route to one destination and a virtual private gateway which learns that same route with that same prefix, and you have route propagation enabled on that route table, you will have two routes to the same destination with the same prefix. And in this case, the static route will be selected as the higher priority, and that one will be used. So this level of selection will always prioritize static routes. But there are situations where you might have multiple routes, both using the same prefix length, and both dynamically learned via route propagation. Well, there's another level of prioritization. For any routes learned via a virtual private gateway, the next priority order is that routes learned from a direct connect are used first, then routes learned via a static VPN, then routes learned via a BGP-based VPN, and if you still have multiple valid routes at this point, so routes that are both learned via propagation, both learned via BGP, and both with the same prefix length, then AS path is used as a decider. An AS path is a BGP term which is used to represent the path between two different ASNs within BGP, and an AS path represents the distance between two different autonomous systems, and so logically routes with a shorter AS path would be preferenced versus those with a longer AS path. So this is an example of basic VPC routing. We have an AWS region with a VPC inside it, two availability zones and two subnets in each, private and public. Then we have two gateway attachments, an internet gateway, and then a virtual private gateway connecting to an on-premises environment on the left. Each subnet in the VPC has one route table attached to it, using the priority system which I've just discussed. In the subnets we've got some resources, so a private instance, a public instance, and a NAT gateway. So let's talk about routing, and this is a pretty typical architecture. On the public subnet we have a route table which uses a default route of 0.0.0.0/0 and a target of the internet gateway. And this means that any traffic not identified by any other route is forwarded to the internet gateway. Now, assuming that both the NAT gateway and the public instance both have public IP version 4 addresses, this means that their data goes out via the internet gateway. Now, the private subnets also have a route table with a default route pointing at the NAT gateway as a target, and this means that for any traffic not otherwise matched, the flow goes via the NAT gateway where it's translated and sent onto the internet via the internet gateway. The route table on the private subnets also has a more specific route, and this route is for the 192.168.10.0/24 network, and it has a longer prefix than the default 0.0.0.0/0 route, and so it has a higher priority. And this means that it's used for any traffic which has a destination of 192.168.10.0 rather than using the default 0.0.0.0/0 route. And this means that data for the on-premises network will leave via the virtual private gateway. So this is a pretty typical routing architecture: public routing via an internet gateway using a default route, private routing using a default route via a NAT gateway, and then access to on-premises networks using a more specific route and a virtual private gateway. But there are some situations where you might have to have something a little bit more complex, and let's look at that next. With this architecture, we have VPC A on the left using 10.16.0.0/16, VPC B on the top right using 10.20.0.0/16, and VPC C on the bottom right also using 10.20.0.0/16. Now there's peering configured between VPC A and VPC B, as well as between VPC A and VPC C, and this is allowed because there's no overlapping CIDR space between A and B and A and C. What this also means, though, is you can't create a peering connection between VPC B and VPC C because there is a CIDR overlap, and that prevents us from creating a VPC peer between those two VPCs. Now let's say that we have some services in VPC B and VPC C, in this case two database platforms running on EC2, and we also have services within VPC A which need to be able to access those database instances. Now one option that we could do is to apply a route table onto both of the subnets in VPC A, and this means that all traffic from VPC A will move to 10.20.0.0/16 via the VPC peer between VPC A and VPC B. So using one route table on both of these subnets will mean that the traffic goes to VPC B whenever 10.20.0.0/16 IP addresses are contacted from VPC A. But what this also means is that VPC A cannot communicate with anything in VPC C because the route will always send data to VPC B. So the peering connection between VPC A and C is not used, and this means that VPC C is unreachable because it uses the same IP address range as VPC B and there's no route to it. So there's no way that VPC A can communicate with VPC C. But it also means that VPC C won't be able to communicate with VPC A because there's no route back for the return traffic. Handling any form of routing when you have CIDR overlaps is a problem, and it's one reason why I always suggest not to have overlapping address space within AWS and any other networks external to AWS. Now, if you do find yourself in this type of situation, there are a couple of easy ways that you can handle it, and that's what I want to talk about over the next few screens. One option to allow access to both of the database instances in VPC B and VPC C is to split the routing inside VPC A, so use a route table per subnet. The top route table applies to the top subnet and the bottom route table applies to the bottom subnet, and this means that the bottom instance will now use the bottom route table, so it can now access the services inside VPC C, whereas the top instance in the top subnet will access VPC B. So by splitting the routing, VPC-B is accessible only from the top subnet of VPC-A, and VPC-C is accessible only from the bottom subnet of VPC-A. So remember, route tables are always defined per subnet. So in this case, we have two route tables that are using the same destination, 10.20.0.0/16, but each of the route tables uses a different target, so a different peering connection between the VPCs. So the top route table uses the AB peering connection, and the bottom route table uses the AC peering connection. So this means that if the top instance in VPC-A attempts to access 10.20.0.10, it will go via the AB peer and access VPC-B. If the bottom instance attempts to access 10.20.0.20, it will go via the AC peer and access VPC-C. But this does mean that the top instance in VPC-A will not be able to access the database instance in VPC-C, and the bottom instance in VPC-A will not be able to access the top database instance in VPC-B, because we have two different route tables that point at different VPC peers that connect to different VPCs. So this architecture means that you have to be very careful about where you deploy instances, because with this architecture, the top subnet in VPC-A will always be limited to VPC-B, and likewise the bottom subnet in VPC-A will always be limited to VPC-C. Now we can do it slightly differently again. Instead of using two route tables, we can stick to using the one, and this route table applies to both of the subnets within VPC-A, and it has two routes contained in that route table. The first route has a destination of 10.20.0.0, and it's a /16 route, and the target is peer AB, so this points at VPC-B. And this means that if nothing more specific matches, then traffic from either of the subnets in VPC-A, if it's destined to any IP address within the 10.20.0.0/16 network, it will be directed towards VPC-B. But we also have another route, the bottom one in pink, and this is more specific. It has a longer prefix. It's a /32 route, which means a single IP address. So both of these routes match the database instance in VPC-C, so 10.20.0.20. So this IP address is contained within the network that the route in blue matches, and it's also the IP address that's directly matched by the route in pink. And so the result of this is the top peer is used for everything in the 10.20.0.0/16 network, which leads to the VPC-B network, except the one specific IP, 10.20.0.20/32, and this uses the more specific route. Remember the priority order, longest prefix wins. And so using this method means that you can point specific IP addresses over the bottom VPC peer toward VPC-C and leave the default being the top VPC peer, which goes to VPC-B. Both of the methods are valid, so this one and using split routing, picking between them is an architectural choice, but you should at least have an awareness of this for the exam. So if you face any questions which talk about routing and overlapping CIDRs, you now know two strategies which you can use to overcome that problem. Now, one more thing that I want to cover before we finish up with this lesson is a relatively new feature which is called Ingress routing. Normally within a VPC, route tables control outgoing or egress routing. So in this example, the application subnet has a default route which sends all of its outgoing traffic that isn't for the VPC CIDR range to a security appliance. Now this security appliance is contained within the public subnet, and this also has an attached route table. This has a default route which sends all unmatched traffic out via the internet gateway, and anything that's destined for the corporate network, so 192.168.10.0/24, through the VGW. So without having the ability to control ingress routing, so without using gateway route tables, any return traffic would arrive at the internet gateway, which would forward that directly back to the service where it originated from. Ingress routing, so using gateway route tables, allows us to assign a route table to gateway objects like virtual private gateways or internet gateways. In this example, a route on the internet gateway would allow us to control ingress routing as it arrived at the internet gateway. So we could configure the internet gateway so no matter what the destination of IP traffic was, to forward that traffic through to the security appliance where it would be inspected and then forwarded through to its intended destination. So gateway route tables, they can be attached to internet gateways or virtual private gateways, and they can be used to direct that gateway to take actions based on inbound traffic, such as in this example, forwarding it through to a security appliance no matter what the actual destination was. So gateway route tables allow us to implement this type of architecture, which allows us to inspect traffic as it flows in and out of the network, so in a bi-directional way. And before we had the ability to assign gateway route tables, we couldn't control it in this way. We could have the traffic flowing through the security appliance on its outbound leg, but couldn't influence how that traffic would be routed when it was returning into the VPC. So this is a really powerful feature that's relatively new to VPCs that you definitely need to be aware of for the exam. So a normal route table is allocated to a subnet and controls traffic as it leaves that subnet. A gateway route table is applied to a gateway object, so an internet gateway or a virtual private gateway, and it's used to influence how traffic is handled on its way back inside a VPC. Okay, so that's everything I wanted to cover within this lesson. I just wanted to give you a reintroduction to the routing architecture within AWS and just provide you with some more complex routing architecture examples, which will be useful to know for the real world and for the exam. Now, don't worry, there is a demo lesson that's coming up elsewhere in this section where you'll get to experience exactly how routing works from an advanced perspective within a VPC and using gateway route tables to control ingress routing. So that will be coming up elsewhere in this section of the course, but this is all of the theory that I wanted to cover. So go ahead, complete this lesson, and when you're ready, I look forward to you joining me in the next.